That's fine. All right, so I'm going to try to tie in. Chapter 8 is actually not that far at all from what we've done already. It just kind of incorporates a lot of things we've done into one little package. And I might try to pull up some websites. I haven't done this yet this semester, but we'll see. I'll show you what I like to do to figure out some recent studies. To see if they show you what we're about to calculate ourselves. To show you that it's out there in the world, right? So help me out. If I knew the mean of something was 28, and the standard deviation is 1.7, and I know that it's normal, what value is bound? It should sound very familiar. But I want to do an example like this just to make sure everybody's got it. Down the middle, 90%. So where do I start with this problem? What do I?
Draw a picture.
No, what? Okay.
Yes, way.
Do it, math one. So I want to get the middle 90%, right? Find the z-scores. And because it's the middle 90%, it's really nice. If I know one, I know the other one automatically. How do I find the z-scores here? I can't look up 0.9. Chart doesn't have a clue what the hell that is. But yeah, there's 10% outside, so there must be 5% on one side. So to look up 0.05,
maybe like 1.645.
you should get, it should be that little asterisk dude.
Yeah.
I like it. So what must the other one be?
Positive.
Positive 1.645 because it's symmetric. This is stuff we could do on this, well, stuff that I could test you on this last test. Right? Now, how do I convert? How do I use these? This is nice for the z-scores, but that's not what I want.
Multiply by the standard deviation.
Yeah, what's the little formula do?
X equals mean plus S.
And let me modify this a bit. Any problem like this is going to really look like this. Does that make sense by itself? Because whatever, if I'm the middle, whatever percent, it's always going to be a positive z-score. That's what the plus sign's doing there. And a negative z-score. That's what the negative sign's doing. So it's the mean, give or take some amount to capture the middle, whatever percent that I want. All right, how's that feel so far? All right. So now I just got to plug stuff in. Got 28, give or take. What's the z? 1.645. See how the negative doesn't really matter? It just matters that it's 1.645 because the plus or minus is in there. It's in there. Okay? 1.645 times the standard deviation 1.7. So to me, what I would do, you don't have to do this. And I always love it when the student asks me where's the plus or minus button, but you just have to do both, right? It'd be kind of smart to calculate this part first. If I knew what that number was, I could just add it to this and subtract it from this, right? So what is this number here? 2.7965. I like it. So I can do 28, give or take that. So then you just have to add it to it. So it'll be 30.7965. 28 minus that would be 25.2035. Haha. Is that, you guys, are you able to get that on your own? Maybe verify that I'm not insane. I just did that in my head. You might.
Negative 25.
No. 28 minus this, so it's still positive. Yeah. So this is kind of like an interval Doesn't it look like interval? Remember good old algebra, interval notation? Don't freak out. We're not doing interval notation, but it is an interval of values. It says that the middle 90% is between 25.2 and 30.8, roughly. Is that by itself decent? I mean, that's nothing more, nothing new. It's a problem I could have asked you on the test, exactly like this. And I actually did. All right, so here's the slightly new thing, but it just uses old information in a new way. How would this change if instead of talking about individual values, I talk about groups of whatever? Let's say groups of size 11. So I want to know between what values bound the middle 90% of all sample means of groups of size 11. What's going to change? What changes when I start taking samples? Standard deviation. So it's going to be the exact same stuff I did here, except instead of 1.7, I'm going to have 1.7 divided by square root 11. I like it. So this is what values bound the middle 90% as far as individuals go, right? Because what's the standard deviation good for? Individuals. So this work gives me 90% of individuals score this to this. And now I'm talking about groups of size 11. So the only thing that changes in our work is the standard deviation I use has to be the one that works for groups of size 11. Nothing amazing. I like it. So then you get 28 plus or minus whatever the shit all that is. 3.89. I don't know. Probably very wrong. I'm okay with it. Get used to it. I'm more like 0.86 or something. I don't know. Ah, that's close. 0.843?
312.
Yeah, 843. I like it. Is everybody cool with this? What's happening right now? I mean, what happens when I take samples of size bigger than 1? What happens when I take the samples? What's the main thing that happens to the image, to the picture? Comes closer to the center. So I shouldn't have to go as far out to get the 90%, because everything comes close to the middle. So look, how far do I have to go out now versus how far I had to go out before? When I take groups of size 11 and I draw the new picture of means, everything comes to the middle because the standard deviation gets smaller. So I don't have to go out as far to catch 90%. Okay, I like it. I like it. Did you have to actually know that to be able to do this work? No. That's good to know. And then you just got whatever the last is. 27.157 to 28.843. All right. So this still isn't quite what we're going to do in Chapter 8. This still isn't quite that. But I just want to show you, this is everything we can do already. This is all stuff we could do already. I didn't ask a question like this on the test, but I actually could have. It wouldn't have been that big of a push from what we'd done before. So here's the new stuff. And here we're finally getting closer to the reality of how we live normally in statistics. Normally I don't know either one of these. But let's start off with admitting that we normally don't know this at least. Now there's a situation where I could know this, but I don't know this. So for example, I know the standard deviation. I could look it up. The standard deviation for the heights of all men in America. You guys with me? But I could take a sample. I could say, well, what about Wisconsin? How are they? They still have the same standard deviation because they still are men in America. Are you with me? But what's their mean? Could be different, right? Okay, I like it. I like it. So here's what's happening. We're going to first start. Now, eventually, we're going to say, what if we don't know either of these damn things? And I like that. That, of course, is going to be. You didn't have to react that harshly. That, of course, is going to be the worst situation. Things are going to get kind of freaky then. Okay? So that's why we start with saying, okay, let's pretend like we know the standard deviation, because that happens sometimes. We just don't know the actual mean. So what I'm trying to do now is, if I didn't know the average height of all the men in Wisconsin, what's the best we could probably do? What's the best we could do? Are we going to be able to talk to every man in Wisconsin? More than likely not. We don't have a lot of resources, right? All of us put together, we're all either a teacher or a college student. So I don't think we have a lot of resources. Are you with me? So what's the best we could do is, of course, take a sample. In which case we are not going to get the mu, we're going to get freaking X bar, which will be our best guess. So here's how this connects to what we just did up here. So over here, if we go to Wisconsin and we take a sample, let's say we take a sample of 106 men in Wisconsin. And let's say we get an average height of 68.81 inches. So now my question is, well, what would be the actual average height of all the men in Wisconsin? So this is what statistics is always trying to do. We're finally getting to this point. We want to use our sample data to make an inference about the whole population, right? And this happens all the damn time. If you pay any attention to politics at all, you know when they say candidate A is going to get 44% of the vote, candidate B is going to get 42% of the vote, and you're like, well, candidate A is going to freaking win. What's at the bottom of the screen always is plus or minus 4% is what it normally is. You guys, anybody ever notice that? And this isn't just a number they made it like, we're not sure, so let's just make some up, cover our ass. No, we're going to learn where that number came from. We're actually going to see the formula that creates that number. Yeah?
Just kind of side note, do they do that for like the weather when it's like raining? Is like a 30% chance of rain? Or no? Is that just something?
The 30% chance of rain is more what the area of land that the models say is actually going to get rain.
Oh.
So like 30% of the area is going to get rain.
Oh,
That's
okay.
one interpretation of it. It could mean a few different things, to be honest. Yeah, so it ends up being a little bit more subjective, because you have meteorologists that will disagree with each other, because they can interpret the data.
Okay.
Yeah. Have you ever? I know we don't get hurricanes here,
Yeah.
but I'm sure I've got family in Virginia, so there's been several hurricanes that kind of went through near there. You ever notice they got that cone, that uncertainty? They have the black line down the middle and the cone of uncertainty, and it grows several days out, right? So, how did I want to relate to the one you said? Well, that'll come up. That's sort of like this. I don't know why I said that. That's sort of like that plus or minus thing, that cone of uncertainty a little bit,
Yeah.
right? I'm not sure why I just brought that up, but oh, I wanted to, so I did. Is that crazy? But yeah, the probably rain. Oh yeah. Oh, okay. This is one. So when you have hurricane, you have several different computer models where you've plugged an equation in. But there's different equations based on which variables you weight the most or the least. Are you guys semi with me? Predicting the weather. You've heard the whole thing. I'm not going to go into the whole butterfly effect. I'm not talking about the movie with Ashton Kutcher or whatever it was. I'm not talking about that. I'm talking about the real butterfly effect, where a butterfly flaps its wings, and because it did, there's a monsoon somewhere, right? So the weather is affected by so many different variables. And you could have an equation with all those variables in it, but somebody else made an equation with slightly different weights on those variables, right? So when they do a hurricane, they actually kind of average all the different computer models. And sometimes they'll show you all the different computer models and all their freaky ass little lines going flying all over the place, and then they kind of average them. So I don't know if you guys ever knew that. It's interesting. And I know I used to live in Florida and Virginia, so hurricanes sort of ruled our lives. There's always tape certain times of the year. There's just always tape on all the windows. But now I live here, and it's fires and earthquakes. Yeah. Okay. That's okay. So where was I? I was in Wisconsin.
Yeah.
And we talked to 106 Wisconsinite men, and we got their average height. And what I want to do is I want to say the real average height of all Wisconsin men is somewhere between this and this. So, what we just did was we kind of altered the stuff a little bit to get this formula. Is this cool? That's basically what we just used there. Now, what part of this do I have to alter a little bit? What part of this do I not know? The mean. I put in place of the mean, I put my best guess, which of course is the sample mean. Okay, so this creates, so if I go and I take 106 Wisconsin men, and I make a sample, and I put together an interval. So there's a real mean of Wisconsin men's height somewhere. There's a real mean of Wisconsin men's height sitting there somewhere. You guys with me? Right now, there's an average height of all Wisconsin men. Period. You with me? Maybe somebody just now died, but earlier they were still there. So their height was included. Are you guys kind of with me? There's an average height. If I go and I take 106 men from Wisconsin, I might get a mean that's here, but then my interval will be like this. Now, if you go take your own sample, will your mean be the same as my mean? No. But if it's 106, it should probably be close to the real mean, right? So maybe yours is over here, maybe. And then your interval looks like this. Now, if I want to be 95% certain that my interval catches the real mean, that's going to relate to the z-score that I use. So over here, where did we get 1.645? That was from assuming I wanted to catch the middle 90%. So if I catch the middle 90% of all the data, how sure am I that I caught the real mean, that my interval actually includes the real mean? I'm 90% sure. Okay, I like it. So here, if I wanted to be, let's say 95% confident that I catch the real average height of men in Wisconsin, how far out will I have to go? How many z-scores? What does 95% relate to? So again, that means I start at my x bar is my best guess, and I go up and down. So far, how far do I have to go to get 95% of the data? Okay, we figure that out. 95% inside means there's how much outside? 5%, which means there's 2.5. So 0.025. If you look that up in your z-score chart, what z-score do you get?
Mine is 1.96.
1.96, I love it. So the real interpretation of this number, though, stay with me now. I went to Wisconsin, I got this mean height. If you go, you're going to get a different mean height. I put money on that. It should still be close to the actual mean height because we're doing a random selection of 106 people. That should be pretty good. But it's not going to be the actual mean height. Okay. So if I use 95% confidence, that doesn't mean anything specific about my own interval. It means that 95% of the intervals that we make, if you make one and you make one and you make one and everybody else makes one, 95% of them will actually contain the real mean. There's a 5% mischance, right? 5% of the confidence intervals that we would make would not include the real mean. That's the actual way to interpret this. So how do I create this sucker? Well, let's see. What do we know? We know x bar. So x bar is 68.81. What's the z-score? 1.96. So I'm going to go up and down. The plus or minus is already built in. So I'm going to go up and down. 1.96 standard deviations. Now, of course, I can't use, I forgot to give you the standard. I think it was 2.5. Something like that last time I looked. 2.5 divided by the square root of 106. I love it. So whatever this interval is that I create, the 95% doesn't really have anything to do with that. Like on a single flip of a coin, So 50% chances ahead. What's that 50% actually say about that single flip? Not a damn thing. That 50% pertains to if a lot of people flipped a coin. 50% of them should show up to be heads around. You guys with me? So the same kind of thing here. If a lot of people made a confidence interval, 95% of them, using the Z-score, 95% of them should actually have the real mean in them. So let's see what we get. 68.81. Give or take. Somebody done that for me?
475.
Ooh.
That's correct.
2.476 yet. All I get. So then I would get 68 point.
334.
Thank you. To
69.286.
69.286. I like it. Inches. All right. So it's not that different from what we just did earlier. When I don't know the actual mu, the actual mean, what's my next best thing? X bar. Now notice this. When do we trust X bar more? How would I make me trust the mean more that I get from my sample? I would just make my sample bigger. Notice how if the sample size gets bigger, this piece gets smaller. So I do hone in on, I feel more and more confident. I have to go less out, away from it. So this part here, we call that part the error. Why does that make sense? Because it's this give or take that. That's how much off I think I am. That's how much off I think this is. So we call this the error. Yes, ma'am?
You repeat exactly like you said it, as the sample size gets bigger.
Oh, as the sample size gets bigger, our error is going to get smaller. So now it's easier for me to say that now I've told you this is the error. And that kind of makes sense. The bigger our sample size is, the more we trust this, the less I have to go away from it to say I'm going to catch the real mean if I go this far. So if I had a sample of size 7, I'm probably going to have to go pretty far out to say I'm 95% sure that the real mean, because I don't trust that damn sample mean much, right? If I just take a sample of size 7, I'm in trouble. If I take a sample of 106, that's why we ended up with an error of less than half an inch, right? Okay, so here's the best thing. You're gonna love you're gonna love this shit. You have to. This is all nuts and bolts shit. This is all plug and chug shit. This is great. But now you gotta write a little sentence about explaining what the hell this is. So here it comes. How certain are we about things in this problem? 95%. I like it. So we are farmers. Now we are 95% confident that the interval 68.33, what was it? 334 inches to 69.286 inches contains the true mean height. Oh, Wisconsin. Men. So there's like a 5% chance that our interval would be one that actually doesn't contain the real mean. So it's sort of a 5% chance that we're wrong. But, 5% chance I'm wrong is pretty damn good for me, so I can live with that. All right, so let's try, let's see, what should we do? Let's try another one. So here, let's say that the mean lifespan of some grizzly bear is, I have no idea. I feel so bad for you, grizzly bear. I have no idea how long you live. I have no idea. Let's say 11.29 years. Sounds probably about right because they get killed by us all the time. And let's say the standard deviation of their height, of the years alive. Oh, I'm supposed to say that yet. Got it. That's going to come later. Sorry. Standard deviation of grizzly bear lifespan. Okay. So we're not going to know the mean. Forgot for a second where we were. So we're going to create a confidence interval for the real mean.
It says the average bear's lifespan is 28 years.
28 years?
Yeah.
I like it. Okay. So I was off a little bit. This was like grizzly bears in a rough area. But see, all right. So that's a perfect example of what this is for. This is like exploratory statistics, especially in the case that we know the population standard deviation. We can zoom in on a certain area and see how off that area is from normal. You guys see what I'm saying? So the 28 thing will come in here in a minute. I'll incorporate it somehow. Let's say that the standard deviation is 6.27 years, just to make something up. Because that one's probably not too available. You can look it up. Try it. I like it. Brenda's my IT guy. So that's known to be that. Let's say we take a sample of what do you got, Jeff? 47 grizzlies, and we observe them, and we note when they die. These poor guys. No idea. This would be a very difficult thing to do, but we're going to just do it in our head, so it's all right. Sample of 47 grizzlies, and we find a sample mean time of life to be 12.27 years. So in some certain area of Canada, let's say, we observe this 47 grizzlies, and we see that they live on average 12.27 years. Are you guys with me? Okay. So we want to know what the actual mean of the whole population of those grizzlies in that area is, right? And then we can compare it to the fact that it's supposed to be 28. I like it. So let's say we want to be. I want to create a 98% confidence interval. CI is going to stand for confidence interval. So whenever you see me asking you to create a confidence interval, it's going to be something plus or minus z times something. It's going to be that format. It's going to be some sample information, give or take some standard deviation stuff. Okay? So there's going to be 3 formulas we learned, to be honest. We've already learned one of them. The one we've learned is this one. And that's for if I know the standard deviation and I want to know what the real mean is. I want to get a feel for it. Okay. So what do I need to do first? What do I know already that my formula requires me to know? Yeah, I know the standard deviation. Sweet. I know sample size. Sweet. I know X bar. Sweet. Right? So sometimes I could, if I wanted to, I could just give you a list of data. And then you plug it into your list in your calculator and you use one var stats and you get your own X bar. Right? But here I'm just telling you what X bar is, just to be nice. So what am I missing? Z. And of course I get Z from where? Yeah, how confident I want to be. Right? So take a minute and try to figure out what the Z is. Good. So Z is 2.33. Why do I not care about the minus plus? Because it's built in. All I really care about is the number, right? Because the plus or minus is built in. So now it's just plug and chug. It's almost too nice to believe. So the work is really just plug and chug. And then you have to write that explanatory sentence. Explain what the hell you just did. So now if we plug stuff in, 12.27, got it. Give or take 2.33 of these. Comes out 2.4 something. So remember, my suggestion to you is to do the error first. I get 2.13. So normally, as a rule of thumb, we take this out at least as many places as this is. So what do I get there? Is everybody sweet? Is everybody got this part? I mean, this. Normally, the only thing I don't know is z. If I give you a list of data, you have to plug it in to figure out what x bar is, but who cares? I gave you x bar, basically. Yeah, 10.14 up to...
4.1.
Yeah. So try to write the conclusion. While you're doing that, I'm going to try to find some examples. Alright, let's see. What do you guys come up with for the statement? Yeah, we are 98% confident.
Yeah. 14.4.
The interval 10.14 what?
Years.
Years.
14.4 years.
So 14.4 years.
True mean.
True mean lifespan. Yeah. Grizzly bears, GBs, in this area. So does that interval include the known average lifespan of grizzlies? No. So what does that suggest is true about the grizzly bears in this region? For some reason, they seem to be dying earlier, right? I like it. Now, you can't just look at a single sample's mean and go, well, that's evidence. Because maybe when we do this work, this will actually go up to 30 or something. So it includes the chance that it's the same as the actual average. But this is saying there's a 98% chance that this interval catches the real mean, which says there's only a 2% chance that the mean is actually this, outside of this interval. That's evidence that it's very different for the grizzly bears in that region. Something is happening wrong. Are they being killed? Are they being hunted? Is there some other predator there that's killing them? I don't know. You guys get the idea for this? It's exploratory statistics. All right, so let me do this. Let me let you guys work on this here. Let's see. Yeah. So one side says section 8.1, and the other side says section 8.3. This section 8.1 side. Just do the first problem. We'll talk about the next thing after that.
Oh my God.